Welcome to GSSI MEMOX Levi-Civita Day. The today program is awarding ceremony, the prize ceremony that will start now at 3 p.m. and Mario Pulvirenti will share that. At 3:30 we will have the colloquium lecture by Felix Sotto, and after the colloquium lecture there is a little coffee break that everybody is invited to attend. So let me give the microphone to Mario Pulvirenti, who will share this first part.
Thank you so much. So, welcome to everybody. I have 2 sheets to trying to remember what I have to say. So let me start by saying that when I was proposed to introduce Felix Sotto for the prize, I accepted enthusiastically because I like very much his scientific production and the way how to approach a mathematical problem. But after a while I realized that it was a difficult task because I was aware of a part of his scientific activity. So in order to introduce him correctly, I have to study. And so it's a problem. And so I started to do what I don't like to do, looking at the internet what else Felix Sotto did. Well, at this point, how to present him? Just by giving the shopping list, the title of arguments, and so I renounced to do this. So let me try to introduce him in a more informal way. So I know him since a long time, probably he has forgotten. We met many years ago in France in a meeting organized by Jan Brenier in a place that he called La Campagne. At that time, Felix was very young, and he started to do something that impressed me a lot, because he started to work to approach PD in terms of Wasserstein distance and gradient flow. And it was a big novelty that impressed me also because I'm coming from mathematical physics, statistical mechanics, and Wasserstein distance was a concept used essentially by the Russian school for equilibrium statistical mechanics, but also for PD. It was a famous paper by Dobrushin using Wasserstein distance. But our Wasserstein distance was what we call W1, while W2 has a lot of structure, and that period started an intensive research along this direction. But in any case, I was impressed by, the work of Felix was something that I like so much. So you have a concrete problem, so you have a model, but then you have to identify the scale which you want to investigate. And then you have to see what are the tools. And sometimes you have to invent a new mathematics. That it was exactly the opposite approach. At that time, many colleagues of us had a different attitude. I know a technique. What is the problem that I able to solve with this technique? And I was impressed by Felix because his approach was, maybe that I'm wrong, but it was exactly the opposite. This is the problem, what is the technique for this problem? And this is a progress. This is a big progress because you invent, as he did, new techniques, a new approach for solving even traditionally problem. So it's impressive because he worked in 2 pi directions. From mathematical side, stochastic partial differential equation, stochastic homogenization, gradient flow, mass transport problems, entropy solution, multi-scale approaches, and so on. And on the other hand, the practical problem were the thin films, hydrodynamics, kinetic theory, crystal growth, viscous film, porous media flow, and many other things. So it's really impressive. And something that I also liked a lot in his activity is his capability of to interact with the people. So in my opinion, the progress of applied mathematics is to try to share knowledge with other colleagues and go together, to progress all together. So this is the reason why, this is also my personal opinion, and this is the reason why I think that it's very good to give this prize to him, also because his approach is very much related to the Italian tradition. From one side we have Levi-Civita, the mechanics, but also the Giorgi, for instance, it's very much related. So he had the interaction with the school of present school of Ambrosio and his group, and so on. And so I think that it's also proud as an Italian mathematician that to have such a kind of link. So to summarize, there are really many reasons for which Felix Sotto deserves the prize. I mean, a sort of vicinity with our tradition. The fact that the methodology of approaching a mathematical problem and the attitude to interact with the colleagues to progress. For this reason, thank you for having accepted this prize, and best wishes. So
I simply will give you the medal, and yes, please.
Thank you very much.
And we okay, open it. It is a standard. And we should try to open this. Okay, there are the equations inside.
Yes.
This is the first one. We have a nice picture by Levi-Civita, which has been prepared by another recipient of the prize, which is Mauro Captora. It is very nice. So you will choose which one you want to make in a frame. The idea of Mauro Captora. Okay, so I think that after these things, we made it quickly. We hear your perspective. Okay. This is yours. No, it's yours.
So we at 3:30 is the lecture. So after this very quick ceremony that we had the pleasure to witness. I still thank Felix for accepting the prize and our invitation to be here. And all of us, we are waiting for 3:30 when Felix will start his colloquium lecture. And the colloquium lecture which touch, you will see many of the points of the mathematical interest he had, and also his intersection with the Italian mathematics. So we are eager to listen the Felix lecture at 3:30. So we reconvene here in, say, a bit less than 20 minutes. So we resume the second part of the Levi Civita Day with the colloquium lecture by Felix Sotto. Felix Sotto has been introduced before by Mario into a large extent, so I don't need to say anything more. The today lecture will touch a lot of important topics of mathematics that touch also problems which are of interest to people in statistical mechanics. For instance, for those of you who are familiar with the statistical mechanics, there are connected papers by Giorgio Parisi. And what is a pleasure for me to underline that one of the co-authors of Felix is an Italian young mathematician, Francesco Mattesini. There is a very strong connection, you will see, as far as I understand from the abstract, with mathematics done by the Pisa School of the Georgi. And so there will be, I hope we will be able to follow, but I think there will be a great fun. So the title is A Variational Regularity Theory for Optimal Transportation. So please, Felix.
Thank you very much. So first of all, let me say that I'm very honored to receive the Levi Civita Prize for several reasons. And one of the reasons is that the kind of the coordinate-free point of view on differential geometry, which he propagated, certainly was influential in a perhaps indirect way, because I'm not used to reading, unfortunately I'm not so much used to reading old papers, but certainly in an indirect way in to my work relating differential geometry and partial differential equations. So that makes me that is an honor. And the other honor was mentioned by Mario Pulverenti in his very kind speech, that I'm indeed I feel indebted to Italian mathematics in many different ways, and what I'm doing is connected to what is happening here in Italy in the past and in the present at several places, and so I always feel mathematically quite at home when I'm in your country. So for these two reasons, I'm very honored to have received this prize. Okay, so this being said, let me start with my talk, and now probably I need some, since I'm already quite old, I need some help with getting the file on the screen. Yes, thank you. And I must say, I'm not very used to holding the microphone. I hope this will, I'm more, yeah, if it's possible, that would be nice. So, so here is the, okay, and I should switch this on. Here is the title of my talk. So it's about optimal transportation, which is by now a really classical subject, and it's about a new approach to regularity theory for optimal transportation, which is a completely variational approach. I will tell you about the famous non-variational approach by Luis Caffarelli in a second. So in a certain sense, what I want to present here, what we developed is so to say an orthogonal approach to that regularity theory, and essentially was started together with Michael Goldman, so a French mathematician, but who also has a very good relationship to Italian mathematics. He spent quite some time in Pisa a while ago, and what I'm presenting is actually joint work with him and Martin Huisman, and then a recent work with Martin Huisman and the mentioned PhD student Francesco Mattesini. So now let me take the chance to switch equipment.
Maybe the other way around.
Great. Thank you very much. That's much more comfortable. Thank you. Okay, so so this is those are the collaborators, and and instead of regularity theory is something quite technical, and I don't want to start with technicalities with regularity theory, but I want to start with an application of the regularity theory, and it's an application to the problem of matching. And I want to start with this, and in a certain sense that's a problem which probably nowadays is mostly of interest because of its applications in statistics, because it's in a certain sense quantifying the distance between what is called the empirical measure and a probability distribution. So suppose you're given a probability distribution lambda on d-dimensional space, and now you draw n independent samples from that probability distribution x1 to xn, and you look at the what's called empirical measure, which arises from these samples, which is defined by taking the Dirac measures at these points and then taking this type of average. And as you know from the law of large numbers or the central limit theorem, this empirical measure should become closer and closer. Which it's a random measure on RD. So it's a measure in a certain sense in two ways. But almost surely this empirical measure, as n goes to infinity, should converge to this fixed distribution lambda. And of course, a very natural question is how close are these two measures for a finite number of samples for finite n? Can you characterize the distance between these two measures? And so one very natural way to measure the distance between two measures is via optimal transportation. So via the Wasserstein distance, to be more precise, which has a very natural statistical meaning, which I'm going to remind you of. But this slide is just reminding you of the definition of the Wasserstein distance, or the definition of optimal transportation, in the way it was formulated by Kantorowicz. So you're given these two probability measures, or more generally non-negative measures, on the same state space RD, which have the same mass. And then you look at all possible ways of coupling these two, the two random variables which are described by this probability measure. So in other words, you're looking at all measures on the product space which can be considered as a transfer plan, as a transference plan from the mass distribution, which is described by the first measure, to the mass distribution, which is described by the second measure. And what that means is just that if you integrate out the second variable, as done here, so in other words, you take the what's called the marginal with respect to the first variable, you get the first measure, the blue one, the measure mu, and if you do it with respect to the second variable, you get the other measure. So that's kind of all possible ways of, in the language of Monge, of transporting mass from one side to the other side. And so associated with this transference plan, you define a transportation or transport cost, which here is the square of the Euclidean distance. So in a certain sense, you look at all the points where you take some mass, all the points x, and then this mass is shipped to some point y, and then it costs the cost you assign to that infinitesimal shipment of mass is the square of the Euclidean distance, and then you integrate overall kind of potential mass transports. And that defines a functional, and you get the Wasserstein distance, or the squared Wasserstein distance, by minimizing this functional. And taking the square is very natural from a statistical point. It's very natural for several reasons, but in statistics, it's in a certain sense just it amounts to finding a coupling of these two random variables that maximizes the covariance. So it's a very which you can see from expanding the square here. Then you get the two quadratic terms, which are, so to say, null Lagrangians, because they only depend on the marginal. And the only interesting term is the cross term x dot y, and because of the minus sign, you're maximizing the cross term, and that just means maximizing the variance. So you seek a coupling of the two random variables in a way that maximizes the covariance. So that makes that's another reason which makes the choice of the square very natural. Okay, so that's I'm sure many of you know about optimal transportation, and that's just a reminder. And now let's make it even simpler, and let's think of the case where both measures you want to relate by optimal transportation are actually discrete measures. So both of them are atomic. So in other words, what you're given is really kind of two sets of points, the green points x and the blue point y, and you want to optimally transport this Dirac measure into the green Dirac measure into the blue Dirac measure. And that, of course, is nothing else than really matching the green and the blue points. So you have to find an assignment where to every green point you associate a blue point, and you want to do it in a way that minimizes the sum of the square distances. So in that sense, the optimal transportation problem is an optimal matching problem. And as is extremely classical, you get one necessary condition for optimality by just kind of picking two green points and picking their two blue images, and looking at the cost which is associated with these two pairs of points. And optimality tells you that if you would kind of transpose, if you would switch the transport, instead of transporting x1 to y1, you would transport it to y2, and x2, instead of transporting it to y2, you would transport it to y1. That should be more expensive, so there should always be this type of inequality. And then again, if you expand the squares, you find that this inequality is equivalent to that inequality, which just sees the mixed term. And that has a very easy geometric interpretation, namely that the vector which connects the two target points and the vector which connects the two pre-image points, that the angle between these two vectors has to be less than pi over 2. So that's in a certain sense monotonicity, kind of a multidimensional version of monotonicity of the support of the optimal map. And I'm sure many of you know that monotonicity, unless you're in one space dimensions, is not quite enough. There is a strengthening of monotonicity, which then in fact is equivalent to optimality, and that's cyclically monotonicity. So it doesn't just suffice to look at two pairs of points, but you have to look at any finite number of pairs of points, and among them you have to be allowed to redistribute, but without loss of generality, you may assume, since the ordering of the points is arbitrary, that this redistribution is just kind of moving, cyclically permuting these points. And that is exactly this type of optimality condition. And again, because you're working with a square, it translates into this type of generalized strengthened monotonicity condition. And that's called cyclical monotonicity, and that's equivalent to optimality. And now what we're interested in is kind of the mesoscopic behavior of matching two random point clouds. And since on this mesoscopic level, we're not interested in kind of the macroscopic behavior of the probability distribution, it's perfectly legitimate to make the assumption that the probability distribution is constant on the level we're looking at. So we have a constant probability distribution. Of course, that doesn't quite make sense in the whole space, but don't worry for this for a moment. Which means that the points are randomly equidistributed, and that amounts to looking at the what's called the Poisson point process. But I'm going to explain that in a second, what the Poisson point process is. So the question I'm going to phrase here, and of course I'm not the first one to phrase it, but it was phrased in the 80s, is how to connect, how to optimally match two independent copies of the Poisson point process. So let me explain to you what the Poisson point process is. So in a certain sense, it's the most random or the most fair way of throwing points into, of defining a random kind of locally finite point set, or of throwing random points into space. And I always like to say that there are two ways of thinking about the Poisson point process. One, in a certain sense, is canonical in the language of statistical mechanics, bottom up, and the other one is grand canonical, so to say top down. The first one is more intuitive. So let's assume for a moment that we would not be in the whole space RD, but we would be on a big torus of side length L. Then the Poisson point process is or its proxy is pretty easy to define. Let's assume that L is an integer. Let's take L to the power D, which is the volume of the torus, independent points which are drawn from the uniform distribution on the torus. And let's look at this point configuration as I've indicated here. So that's a random point configuration of L to the power D points. And now it's classical that if you let L go to infinity, so your artificial size, if you let it go to infinity, that this kind of point cluster valued random variable converges to something which is the Poisson point process. Now it's a random point cloud in the entire space, which is characterized by two properties. Whenever you take a set omega, let's say open and of bounded measure, then there is a random variable which is attached to the set, which is exactly the number of points which you have inside the set. And the postulate is, or the outcome of this limiting process, is that this number is Poisson distributed with intensity given by the Lebesgue measure of the set omega. That's the first postulate, or the first part of the characterizing property. And the second part of the characterizing property is if you take a disjoint set, then these two random variables are statistically independent. So that's kind of the top-down macrocanonical characterization of what the Poisson point process is. And typically, here we always think of kind of unit intensity, which means that in my way of viewing it, the points have distance of the order of 1. Of course, somewhere outside there can be big holes. Somewhere outside, many points can be close together, but on average, they have distance 1. Okay, so now the question is, let's try to match these 2 let's take 2 independent realizations of the Poisson point process, and let's try to match them in an optimal way. I cannot write down the variational problem because the energy would be infinity, but I can ask that it's cyclically monotone, which in a certain sense means whenever I do a finite change, I only increase the energy. So that makes sense. So let's ask that question. And then if you look at that question in the simplest possible way, in the simplest possible case, when you're dealing with the one-dimensional Poisson point process, so in which case you would just have random points on the line, then you realize that something strange happens. Of course, in this case, cyclically monotone means monotone. And that means once you kind of fix one pair of points, all the other ones are determined because of monotonicity. So there is, in a certain sense, one degree of freedom which you have by kind of picking out, let's say, the point which is closest to the origin, and then saying, okay, this one should go to the point which, let's say, is also closest to the origin upstairs. And once you make this choice, everything to the left and to the right is determined by monotonicity. But now when you do that, you will realize that what you're doing looks not very, I mean, doesn't look very good, that in the sense that for a while, kind of points will not be transported by lot. But then the further you move out, you realize that the transport distance, the displacement, becomes larger and larger, once in this direction, once in this direction. And for experts on Brownian motion, of course, they would not be surprised to hear that the typical displacement as you move out grows at the square root of the distance to your origin. So in a certain sense, doing that in the one-dimensional case is something quite bad, or has this kind of not so nice behavior. So here again, it's repeated. And so what's the reason for the fact for this kind of not so nice behavior? The reason for this not so nice behavior is that the number density of the Poisson point process is a pretty fluctuating quantity. So if you ask the question, so you have your Poisson point process, one realization of the Poisson point process in d dimensions, and you divide up your entire space into boxes of side length L, and think of L as being large, then of course you have a random number of points in this subset, in your finite element, if you want, in your RVE. And of course, the number density, since L is large, will be close to unity. So if you divide the number by the volume of the box, that will be a number that's close to 1. But it's a random number which fluctuates around 1. And the fluctuations are of the order of what we would say CLT scaling, central limit theorem scaling, 1 over the square root of the volume. So those are the fluctuations of the density of the numbers. And then now you realize that higher dimensions is beneficial. If you're in higher dimensions, the fluctuations have, in a certain sense, a better and better scaling, in the sense that they decrease more rapidly as you make L larger. And there is a very kind of convincing back of the envelope argument, physics argument, which tells you that dimension 2 is probably the most interesting dimension. And the argument goes as follows. So let's think of two neighboring boxes of this kind of artificial lateral size L, as I've indicated here. And let's first look at the left box. And the number of points in this left box, in a certain sense, might be a little bit above average, or below average. Let's think above average. So there is, in a certain sense, a certain number of excess points, and by this observation, the number of excess points is, of course, much smaller than the total number of points, which would be of the order of L to the power d. It scales like the square root of that number. That's again the CLT behavior. So there will be, in a certain sense, this amount too many points in the left half. So now the blue points have to, in a certain sense, absorb this excess number of points. And if you want to have a matching that doesn't stray too far away, you would like the blue points to sit in near to the kind of left box, so in a boundary layer of width 1. So how many points do you have in a boundary layer of width 1? Well, that's L to the power d minus 1. And now the question is, how do these two numbers compare? And you realize that in dimension d larger than 2, there's always enough space, enough kind of welcoming points in the boundary layer to absorb your excess points in the left half. So that should be fine. In dimension 1, it's the opposite, and we see that up here. And in dimension 2, you have exactly the same scaling. So the question is, the most interesting question is what happens in dimension 2? And so before giving you the answer, let's make one additional postulate on how to match this thing, and that's perhaps the that's extremely natural postulate, but it requires a certain twist of mind to formulate it, and that's what's called stationarity. So stationarity is one word, one of the possible words of saying that something is statistically translation invariant. And so, for instance, the Poisson point process is statistically invariant, meaning that if you take a point configuration and you shift it by a deterministic vector 10 meters to the left, that new point configuration has the same law, is distributed in the same way. So in a certain sense, in the Poisson point process, you cannot, there is no point, I mean, there is no origin. It looks the same everywhere. That's stationarity. And now you impose exactly the same thing on the matching. So the matching is nothing else than kind of a point cloud in the product space where you just consider those green and blue points that are being matched, and you want this point cloud to be also stationary, so you want the matching to be statistically translation invariant. That's a very natural requirement on the matching. And so exactly this type of question originated in the Hungarian Budapest School of Combinatorics in the 80s, and then was taken up in probability theory, and for instance, Talleyrand was somebody who started and is still working on this type of question. But then that's the nice connection to Italy, that in Pisa both kind of the physicists and the mathematicians got interested in this type of in this matching problem, and there has been recent work by Cariaciolo, Parisi, and co-workers on heuristics of the 2D case, and then kind of made rigorous by Luigi Ambrosio and his group. And so, but the question I want to ask is kind of this very precise question: is there what happens in the two-dimensional case? Is there a way of matching in a statistically translation invariant way and in an optimal way, in the sense of cyclical monotonicity, two independent copies of the Poisson point process in dimension larger than to my co-worker, together with my former colleague Karl Theodor Sturm, proved that this is the case, and that's a variational argument, a little bit like in homogenization, the construction of the corrector or the gradient of the corrector. You lift to probability space, you forget the spatial variable, and then you can prove this. And yes.
Is it related to this threshold equal to the fact that the excess point and boundary layers are comparable?
Yes. So the intuition. Sorry. The intuition why the two-dimensional case is special is exactly this one. That in a certain sense, the higher the dimension, the less the relative size of the fluctuations, and the better kind of nearby boundary layers. So the boundary layer is in a position of taking up your points. So that's exactly this is exactly, and it was already given in the first Hungarian paper, that's exactly the intuition why the two-dimensional case is kind of the critical case. And but yes, so the way I would phrase it is that due to the random nature of the Poisson point process, there might be too many or too little points in one box. So in a certain sense, there might be quite a number of less green points or more green points than blue points in this box. So it's clear that these excess green points have to be moved outside of the box. So now the question is, can you do that without moving them far? And that can only be possible if not so far from the box you have enough blue points to welcome them. And so therefore it's natural to compare this number of this typical number of excess points with the number of welcoming points in the vicinity. And that leads you exactly to comparing these two exponents, and if d is equal to 2, they're exactly the same. So it's really kind of this heuristics which explains that the two-dimensional case is critical, but then it's not clear whether it still works in the two-dimensional case or not. So there's always the question at the critical dimension, what actually happens at the critical dimension, or what happens at the critical point. And the answer is that at the critical point, it does not work. So the 2D case is like the 1D case. And so that's an application of this regularity theory for optimal transportation, which I would like to advertise. And before giving you this regularity theory in more detail, let me tell you how we used it in this matching problem. So again, I will postpone this more technical part of regularity theory towards, if I still have the time, the last part of my talk, and tell you now how we prove this non-existence result. So in the two-dimensional case, the 1D case is obvious. So how we use our regularity result, and in fact we use the regularity result in form of a harmonic approximation result. And in a certain sense, what I want to advertise most is this harmonic approximation result. And I also want to advertise it here, and it's a pleasure to advertise it in Italy, because it's very in the spirit of what de Giorgi's strategy for regularity theory of minimal surfaces, which also at a crucial point has a harmonic approximation result. Okay, so but here is on three slides how we argue for this non-existence result. So I don't know whether it's a good idea to try to give this proof, but I want to tell you at which place we use this harmonic approximation. So we assume that there were such a cyclically monotone stationary coupling, and we want to get a contradiction. And so there are two easy consequences. So first of ergodicity, that if we have such a coupling, we know that, and now we look at a subsystem of size L, we know that most points are not transported by lot. So that's a qualitative statement we start with. And then we use monotonicity, which tells us that the fact that most particles are not transported by lot means that the remaining particles cannot be transported a huge distance. So all the remaining particles in this kind of ball of radius L can only be moved by little o of L. And in the end, the contradiction will be, relying on the difference between a big O and a little o. And so that in particular means that if we look at the local transportation energy, so if we look at all the points x in this ball, and we look at all the image point y, and we sum over the square of the transport distance, and we average over the volume, then this is little o of L square. And that's a kind of a non-dimensional smallness, because the left-hand side has units of length square, and here we have a kind of a little o with respect to a length square. So that tells us that something is non-dimensionally small, and we would like it to be much, much smaller, because in a certain sense we know that the points are extremely, not extremely, but they're pretty much uniformly distributed, in the sense that if we look at the distance between the empirical measure of one of the two copies, let's say the green one, inside the ball of radius L, then this empirical distribution is pretty close to the uniform distribution. Again, we normalize by the volume by just a logarithm. So we know that in order to connect this random point cloud inside a box of size L or inside a disk of size L to a uniform distribution, we need to transport the points at most by something that grows logarithmically, or like the square root of the logarithm in the size of the box. And that's an upper bound, which, for instance, comes out of the work by the PISA analysis group. And now, in a certain sense, there is a little bit of a mismatch that these points are very close to uniform in this sense. But in fact, a priori, we just know that the transport distance is little of L square. And what we have to do is to transmit the smallness of what I like to call the data term to the smallness of the energy. And that's exactly where our harmonic approximation helps us. So here again is the definition of something like the local energy and the local data size. So that's the local transportation cost. That's the measure of how far our empirical measures are away from the uniform distribution. So this a priori is much smaller than this one. And in the end, we want to show that also the blue quantity is as small as the green quantity. And the way we do that is by harmonic approximation. So an output of our regularity theory is that we know that there is a harmonic function so that the displacement is close to the gradient of the harmonic function. That's the crucial harmonic approximation result, which comes out of our regularity theory, that displacement is close to the gradient of a harmonic function. And then we can use kind of basic regularity theory for harmonic functions to tell us that the smallness of the data term transmits to the smallness of the solution. And that's the main step. And then there is an easy contradiction which has to do with the fact that now we know that the transportation distance in a ball of size L is in fact little o of the square root of the logarithm, but then there is a lower bound which tells us it has to be at least the square root of the logarithm, and that's the contradiction. So the contradiction, really not surprisingly in the critical case, is a very thin line which is based exactly on a logarithmic behavior. And the key step is this harmonic approximation. So now I want to tell you about this kind of the regularity theory behind this, which leads to the harmonic approximation. How much time do I still have? So therefore I was a bit non-committal. Here I say take any constant so that they have the same mass. So when uniform doesn't mean 1. So here the total mass is L to the power D, because you have about L to the power D points, not exactly L to the power D, but close. And here you have a constant which is close to 1. No. I mean, I'm adjusting the constant here so that these two measures do have exactly the same mass. Yeah. So therefore, I write uniform, which doesn't specify the value.
Sorry, I suppose it was okay.
Yeah.
Sorry, I don't get in one dimension. I mean, you showed this picture that somehow locally you get a nice matching, and then if you globally, because of the fluctuation, things get worse and worse. But why you cannot do this in why this doesn't give you something cyclic monotone, and why it will not be stationary? I mean, you have two choices somehow, taking the nearest to the left to start with and the nearest to the right, and then somehow go on up to infinity. Why this doesn't give you a stationary process if you somehow choose this one half, I don't know, each of them or something like that?
That would, I mean, you can, I mean, I'm not really sure whether I completely understand what you're saying. So, what do you mean with one half? I mean, now I'm in a certain sense poised to. I mean, of course, I could split this up a little bit to the left and a little bit here, but that wouldn't kind of take away this effect. I mean, that would be just, in a certain sense, that would do something. On the level of distance of the order of 1, but it wouldn't overcome this this L to the power 1/2.
But why is this not cyclically monotone? I mean, they're all going in the right direction.
But so I mean, if I understand you correctly, you're saying let's put this point one half here and one half here. Let's put this point one half here and one half here. Is that what you're saying?
No. I mean, just the first one, and then you have no choice anymore. No, I mean, then the cyclical monotonicity forces you what to do. No?
Yeah.
I mean,
so then I don't understand what alternative plan you're suggesting.
I mean, you choose the first one, and then somehow the first on the left, and the other choice is the first on the right. And can't you do that?
No, you want to connect this one to something here? But then that certainly would violate monotonicity, because it would kind of contradict this. I think it's probably better to do a picture and then discuss it. Yeah. But thanks, so let's discuss that later. Okay, so so now regularity theory. So I mean, it's absolutely classical that the optimal transportation is connected to a partial differential equation, which is the Monge-Ampère equation, and which one way of seeing it is here. So remember, optimal transportation minimizing this cost functional overall admissible plans that connect one measure. Let's take the second one to be a Lebesgue measure. Cyclical monotonicity can be rephrased by saying that the support of this measure on the product space is contained in the subgradient of a convex function, the Kantorovich potential, and solution of the dual problem. And then the fact that the marginals are right can be expressed in terms of this condition here, which tells you that the gradient of the convex function, which exists Lebesgue almost everywhere, if this here has a Lebesgue density, that's fine, pushes forward the measure mu into the Lebesgue measure. And then if on the right-hand side you use the transformation rule and you use the fact that the test function was arbitrary, at least in situations where everything is smooth, you find that this leads to this equation, which is an equation on the derivative of this map, which is the Hessian of the potential, which is a symmetric positive semi-definite matrix, and it gives rise to a condition on the determinant of this matrix, which has to be equal to mu. That's the Monge-Ampère equation. And that's a famous partial differential equation because in a certain sense it sits at the cross-section of two cultures of PDE. The variational setting, after all it's the Euler-Lagrange equation optimal transportation, and the world of maximum principle, fully nonlinear elliptic equations, viscosity solutions, and so on. So it's an elliptic, in this world, it's an elliptic equation because this functional on matrix space that defines the PDE has this monotonicity property, which means the comparison principle holds. But it's degenerate, and its degeneracy is intimately related to the fact that the equation has a much larger invariance group than the Laplace equation, which just has rotations as invariance group and reflections. The Monge-Ampère equation is so affine invariant, and and the degeneracy, in a certain sense, is a price to pay, which comes with this regularity, with this invariance group, and therefore, what's the difficulty in this equation? You may, for regularity, you may satisfy this equation in a strange way. So, I mean, it tells you that the determinant of the Hessian, which means the product of all the eigenvalues, has to be equal to 1. But that's a condition which you can satisfy if some of the eigenvalues are very close to 0 and the other ones are very close to infinity. So it doesn't a priori give you control about the spread of the eigenvalues. And that means your solution might be might have extremely anisotropic level sets. And in fact, there is an easy example, I mean, inspired but not difficult example by Pogorelov, which shows that starting from dimension 3, you can write down honest viscosity solutions which are not smooth, which have exactly this phenomenon. And Caffarelli's amazing result was that this is the worst case that can happen. These counterexamples, in a certain sense, are the generic behavior, and therefore any singularity must connect to the boundary of the domain, and then you can impose conditions on the boundary data which rule out this behavior. And that's exactly what was at the kind of origin of his regularity theory for first for the Monge-Ampère equation, and then as a consequence for optimal transportation. And but it's also well known that generically optimal transportation doesn't give you smooth solutions. Even so, here is a classical example of two sets that have a smooth boundary, and now you ask for the optimal transport of the characteristic function of one set to the other set, and it's known that this has a kind of a singularity, and that's a very kind of easy, robust argument. And if you're in kind of if you don't work in RD but you work on manifolds, then there are even more generic origins of irregularity, and therefore it was very natural that Alessio Figali and co-workers started thinking about what's called epsilon regularity. So can you show that if, and that's again something which which I think was started by De Giorgi for minimal surface theory, can you show that if your solution in a certain sense on average is small, that it's actually smooth in a slightly smaller domain? That's epsilon regularity, and that's exactly what Figali and Kim, and then later De Filippis and Figali proved for optimal transportation, that if in a certain non-dimensional way your cost is small locally and your densities are smooth, then also the Kantorovich potential is smooth. And in a certain, we proved they used Caffarelli's theory to prove this epsilon regularity result. And we, in a certain sense, reproved it under more robust conditions via the harmonic approximation. So here again is the second time it comes. So what we're showing in order to get this type of epsilon regularity result is a statement of the type that if in a non-dimensional way and locally the transportation distance is small and the densities are well behaved, then the displacement is close to the gradient of a harmonic function. And now on the next slide, I want to give you the precise statement of this result, and then I want to tell you in 1 or 2 slides what the idea of the proof is of this harmonic approximation result, and then I guess I will have to stop also eventually. So here is the kind of the harmonic approximation result in its kind of technical formulation. So the nice thing is that it holds for 2 completely general measures, and it's exactly this generality which we need for the matching problem, because remember, in this case, both measures were actually Dirac measures. So the statement here, I'm using the same notation as in the matching problem. There is something like the local energy. So the energy that's related to all the particles that get moved out of, that start in the ball of radius, let's call it 6, or end up in the ball of radius 6. You look at all the cost that's involved in these particles, and you look at the corresponding data term. So you look at how close is the restriction of your measure mu on the ball of radius 6 to the right constant, so that these 2 measures have the same mass, restricted to the ball of radius 6, and then you also account for how far this constant is from 1. And you do it in the Wasserstein topology. So you measure how close your measures are to a uniform measure locally in the Wasserstein topology. And the statement is a typical analysis statement. For any threshold tau, there exists a barrier epsilon, which just depends on tau and the dimension and a constant, such that if the local energy and the local data term are below this threshold, then you can say something interesting. And the interesting is that there exists a gradient of a harmonic function. It's a little bit more general, so only the gradient is harmonic component-wise, such that the displacement is close to the gradient of this harmonic function in this very same expression which defines the local energy, now on a slightly smaller ball, with up to a kind of a tiny fraction of the energy. So this term is really much smaller than this term, and that's the tau which you're free to choose, plus a big constant in front of the data term. So that's the harmonic approximation result. The displacement is close to a gradient of a harmonic function if you're in this small, in this epsilon regime. That's really the core result of what we're doing. And now here comes a little bit of fake mechanics. The way we prove it is not in the Lagrangian picture, not in the particle picture, but the way we prove it is in the so-called Eulerian or dynamical picture, the dynamical formulation of optimal transportation, which was formulated by Yann Brenier and Jean-David Benamou, which I guess some of you are familiar with, which means that you can rephrase the Wasserstein distance, now I would have said as a geodesic distance, but you don't even need that, as kind of a variational problem where you look at kind of all ways of connecting the initial to the terminal density. There is some fake time t, and you express this path in density space via the continuity equation, which involves a flux J. And what you have to consider is what would amount to the kinetic energy density in this problem if it were a mechanical problem. And so why is it not surprising that this formulation is much better than the original Monge or even the Kantorovich formulation? Because it reveals convexity. It reveals kind of some amount of, in fact, strict convexity, because the simple function which associates to pair rho positive number and a vector j, this expression is not just a convex function, but in many directions it's strictly convex. And it's that strict convexity which is driving regularity theory. I mean, those who do calculus variations know that strict convexity is your friend in regularity theory in the calculus of variations. And that's exactly our idea, that based on the strict convexity, we linearize the variational problem around rho equal to 1, which means essentially dropping this term, which amounts to replacing the Wasserstein distance by an h minus 1 by negative Sobolev distance. That's an old observation that you can somehow make a connection between these two, and that's really what's driving this harmonic approximation result. So we go to the Eulerian formulation, and we construct a kind of a harmonic function such that its gradient approximates the Eulerian velocity in this sense. So that's just a reformulation, an Eulerian reformulation of the Lagrangian result before. And so how that's the last slide. So how do we get this harmonic function? Almost previous to last slide. How do we get this harmonic function? Well, we have to solve, an equation for the Poisson equation. We have to come up with some boundary conditions for the Poisson equation. And now, what are the right boundary conditions? The right boundary conditions are flux boundary conditions, so Neumann boundary conditions, because we're comparing the Poisson equation to kind of this kinetic, this transport equation, which also naturally has flux boundary conditions. So what we do is we go onto a ball of radius r. We look at the flux boundary condition we get from the optimal transport side, so the normal component of the flux J, which we call F. We can't take this as the boundary conditions because that's still a function which depends on time next to depending on where you are on the boundary of the ball. So you have to average it in time, but that's exactly what you take as your Neumann boundary conditions for the Poisson problem. And it's exactly this this solution of the Poisson problem we take, and which is close to the velocity. And so there is kind of choosing a good radius, which plays a role here. And so that's really the previous to last slide. So that's just a slide of, perhaps it's not, I will not spend much time on it. Because anyway I already said it, that this type of regularity theory is in spirit very close to what Giorgi, this type of epsilon regularity theory is very close to what Giorgi advocated or kind of carried out for minimal surface theory. And there's one article by Schön and Simon where this becomes most pronounced, that in this case of minimal surfaces, you're comparing your minimal surface, provided it's already flat, to the graph of a harmonic function. And you take exactly the same boundary conditions, but you run in similar problems because you don't know a priori that your minimal surface is a graph, so the boundary is not really a graph. So yeah, there's a mismatch between the description of boundary conditions, very much like in the optimal transportation problem. We also have this mismatch of needing to average in time. And that you overcome by lower dimensional isoperimetric problem, very much like in the minimal surface theory, to show that this gives you only a higher order error. Okay, so let me skip this and essentially stop here. So there are a couple of classical applications of this variational approach to regularity theory, which we used, and where we essentially show we can do the same thing. But I think what's most interesting is the fact that this approach is robust enough to handle these very singular measures which come up in the matching problem. And I think that is the area we want to push further. We also want to kind of connect to p-cost functionals, which I think is a very natural question, whether one can develop a regularity theory also in this case. So let me stop here, and apologies if I was over time. You didn't get the chance to answer the question how much over time I was already.
Time for questions. Who's the first one? Dimitri.
Yes, thank you very much for this nice talk with so much information. If we make a small perturbation of the Poisson measure and we consider hard spheres, non-overlapping spheres of some, say, size epsilon, which might be order 1, but as small as we like, the matching problem is still d equals 2, maybe not, or I don't know if you have thought of that, and what would be the harmonic approximation in that case?
So my gut feeling is that if you kind of constrain the Poisson point process to have this non-overlap condition, of course you're making it slightly more uniform because you're preventing kind of very dense clusters, but I don't think that this will kind of overcome this basic scaling. So I would expect that even for this type of modification, you would have non-existence in the two-dimensional case.
D equal 2 would be again the critical...
I think so. You would have to pass to something which is called hyper-uniform.
Hyper-uniform.
If you have hyper-uniformity, then so it's more a large scale than a small scale problem.
Okay.
And so therefore, and I'm pretty confident that our techniques would be able to show that, because the core of the technique is completely deterministic with this harmonic
So the
approximation.
harmonic approximation would be similar for...
Yeah, so I mean, what we, in this application to the matching problem, what we really use is this completely deterministic result, which is oblivious to the structure of these measures. You just need that they're sufficiently close to uniform, and so therefore the technical ingredient is completely deterministic and robust, so that I would expect.
So if you don't couple Poisson processes, but you couple these perturbed with the spheres, so the macroscopic somehow techniques wouldn't change much.
Exactly, because in a certain sense we're using this harmonic approximation result in form of a large-scale regularity result, like in stochastic homogenization, where kind of large-scale regularity is a key concept.
Okay, thank you.
Other question? If not, can you argue a little bit? You're talking about thermodynamic limit in d equal 2.
Yeah.
As a future part. What do you expect?
So what we hope. So it's clear that that in the 2D case, as you let the size of your torus go to infinity, your transportation distance will diverge. But what we would hope to be able to say is that if you look at the increments, so if you look at kind of a pair of points and two words transported, that the increments, that this quantity does not diverge and in fact has a stationary limit. And the analogy is again stochastic homogenization, the 2D case where you know that the corrector itself is not stationary, but the gradient of the corrector is. And so here we would hope to be able to show in this much more nonlinear problem that increments of the optimal transport converge to something stationary, and that's what's meant here.
Further questions, please? If not, let's thank Felix. Thank you very much to all of you, and we close today's session.